thing in my spare time. At least one of the things that I like to do is mess around with computers, play a little bit of CTF. CTFs are a lot of fun, and that's actually one of the places where my knowledge of assembly language comes to most frequent need. And I'm really frustrated when things feel like a black box. And the reason that that's important is that's why I got interested in learning assembly language in the first place. I took a class in how to program in BASIC when I was, 12, something like that. And that was cool and all. And then I got distracted from computers for a year or a decade or so. Got back to it, about 5 years ago. Started doing Python and Bash. And especially Python, it had all of these functions and batteries were included, and that was awesome. And I still think Python is awesome, but so much of it felt like a black box to me. So I started learning some C. And, that explained some of the stuff that was going on under the hood of Python. But I still felt like something was missing. I still felt that there were things in C that, okay, I want to know how this works. And the nice thing about assembly language is, since, you're making all the system calls, you're putting all the pieces of information into memory, you're doing every little bit, there really is a minimum of hand waving when you're doing assembly. And so it's tedious. It's not, the most practical thing for writing a large, full-fledged, full-scale application, but it teaches you a lot about how things work, and it doesn't feel like a black box. Now, what is assembly language? It's not quite machine language, but it's close. A computer, it understands 1 and 0, on and off. Certain sequences of that mean certain things to the computer. Of course, you're not going to remember, 1 0 1 1 1 0 blah blah blah. No, none of us can memorize that. But you have instructions in assembly language that are mnemonics for machine code instructions. And so, it's basically machine language in a way that humans can understand it. There's usually a 1-to-1 correlation between a machine language instruction and an assembly language. Occasionally it's not, but it's usually 1-to-1, and we're not going to get bogged down in the minutia here because we only have an hour. It varies by processor. Different processor architectures have different assembly language. We're going to be discussing 32-bit X86 today, but if you're curious about learning a different kind of assembly language platform, hopefully what you learn today about memory and registers and instructions and system calls will serve you in good stead if you decide to explore assembly language on another architecture. Now, I guess I touched on this a tiny bit about why to learn assembly language when I was talking about why I personally started to pick it up. Why would you want to learn this? For one, some information security disciplines require it. If you want to go into anything that involves, reversing, binary analysis, malware analysis, things like that, you're really going to need to be familiar with assembly language, because otherwise, how are you going to figure out how it works? You throw it into a disassembler and, it's going to disassemble into assembly. There are some disassemblers that will, come up with pseudo C code, things like that, but sometimes that gets a little wonky, and you might still want to dive down deeper into, okay, what instructions is this actually executing? And to do that, you're going to need to know assembly. Or, you might want to learn it for the same reason that I learned it. I was just a little curious about some of the lower level details of how my code worked, how my programming languages worked. Finally, it's fun, it's challenging, it's nice to be able to see what you can do, see what you can program, see if there's something fun that you can do with as few crutches, as few black boxes as possible. It's good for the curious. Now, a few words on how assembly language works. We're going to be getting into the coding soon enough, but first, how does it work? Basically, you're interacting with memory. And so you want to know, okay, what parts of computer memory does assembly language commonly access? And then how do you access those parts of computer memory with assembly language instructions? Now, what parts of memory are you going to be talking to? Well, there's, what you normally think of as memory, like either, RAM or virtual memory. That's where you've got, that's where you've got the heap and the stack. That's where you've got the data that your program is going in and talking to. And then there's also memory on the CPU. A lot of times, that's not the first most intuitive thing that comes to mind as far as memory, but a lot of the memory that you're going to be talking to and interacting with when you write assembly code is registers on the CPU. What the heck is a register? I will be getting to that shortly. The heap and the stack are the main structures in RAM that you're going to be interacting with. I would say the stack more than the heap. The heap is where global variables that are allocated at compile time are stored. Think of it as, it's kind of like a bookshelf, but you can't really, when you take a book out, you can't squish them together. So there can be a lot of, jumping around when you allocate a little bit of memory off the heap. You take a book out, but you still may need to jump around. You may not actually have all of the space you need to store one structure in the same place. I'm touching on that for completeness, although since this is a, assembly language 101 talk, we're really going to be talking more about the other main structure, the stack. That's where you store local contextual type variables, the local variables to a function, for example, stuff that you define while it's running and then pop it off the stack and use it for other purposes. It's kind of like a card game discard pile. You're playing Go Fish or whatever. You can either take the top card off of, the stack of shuffled cards, or you can take something off the discard pile. You can take the top card off the discard pile. You can throw a card on top of the discard pile to then be taken off by the next person. But you can't rifle through the middle of the discard pile. If you've got three things down in the stack, the only way you're going to get to that is by, popping the things off of it, 1, 2, 3. You can't just take number 3 and leave the rest alone. You will use this when you're coding assembly a lot. We're going to deal with some stack operations in some of the code that I'm showing you today. Now about those registers that I mentioned. That's memory that's on the CPU. It's awesome because it's fast. You can get to a register like that. It's the fastest place that the CPU can access data because it's right there. You don't have to go talk to the RAM or anything like that. It's right there for you to grab. The thing that's a pain in the butt about the registers is that they're very, very small. They're only going to be as wide as the data bus. So on a 32-bit architecture, you got 32 bits in each register. 64 bits, you have access to 64-bit registers. If you're doing a 16-bit processor, the registers are generally 16 bits. So yeah, they're great because they're right there, and when we get into system calls, actually interfacing with the operating system, there are specific registers that you put values in. It's okay, it knows to call these system calls, but they're small. You're not going to put a string in a register. You're going to put, say, the address of a string. It's, understanding pointers is key to be able to function in assembly language because you can fit a pointer, you can fit an address of a piece of data in a register. You're probably not going to be able to fit the data itself into the register. Now, what are the registers? First of all, there are the general purpose registers. There's EAX, EBX, ECX, and EDX. Those names go back to older architectures, the accumulator register, base register, counter register, data register. The only really one of those names that I tend to use the register for that purpose on a regular basis is I will usually use ECX as a counter, but even then, you might not sometimes. And I say that I use ECX as a counter. There'll be a piece of code today that you'll see that I use something else as the counter because the system call requires something else other than my index in ECX. Again, these are in 32-bit assembly, these are 32-bit chunks of data. You can access parts of registers. For example, EAX stands for extended AX or extended accumulator register. AX is just the bottom 16 bits of EAX. AL is the lowest 8 bits. There's also a partial register called AH, which is the higher order 8 bits of that lower 16 bits of the 32. Don't get too bogged down in that. I mean, I don't really use AH all that often. I use EAX, AX, and then AL when we'll get to that later. The lower order registers are useful in avoiding null bytes when you're trying to write shellcode. Stack and base pointers, ESP and EBP, those tell you where the base of the stack and the top of the stack are. Those are especially important for being able to find and access your data on the stack, or messing around doing funny things on the stack if you're writing exploits. And then there's the index registers ESI and EDI. Those did have a purpose in a lot of the older architectures. They were the registers where you could put pointers. Now, though, it's a little more forgiving in 32-bit X86. Those are honest-to-God general-purpose registers where you can shove whatever kinds of pieces of data you want. Like, they're nice to hold things, save things, move them around. In addition to those general-purpose registers, there are a few other registers. There's EIP, which I'm sure a lot of you have heard people talking about. That's the instruction pointer. That is the address of the next instruction that the computer is planning to follow. And a lot of times when you're writing or executing exploits, the whole goal is to overwrite EIP. Because if you have control of EIP, you have control of the next instruction that the computer is going to follow. So if you point it to your code instead of the next legitimate piece of code, it's going to run what you throw at it, not what the original programmer intended. When you're writing a buffer overflow exploit, for example, you put enough junk in the buffer that it overwrites EIP, and you go to town. There are other registers, flags, segment registers. I'm just mentioning those for the sake of completeness if you want to look those up, but for Assembly Language 101, you're really not going to be dealing that much with those registers. Like I said, just mentioning them for the sake of completeness. Now, okay, you know about what the stack is, about these little chunks of memory, the registers in the CPU. How in the heck do you talk to them? How in the heck do you put data in them? You got instructions for that. Move is probably the most basic instruction. That was definitely the first one I learned. And it moves a piece of data into a specific register. I've got the syntax here just so you know that you might see either AT&T or Intel syntax are the two that are, I would say, the most common. Everything from here on out, everything I'm going to show you is going to be an Intel syntax, just because, even though I think AT&T is a little more intuitive in that you're moving, you move the value to the place. I really don't like all those extra % signs and $ signs, and I don't want all those junk characters in my code. There's enough obfuscated crap for me to look at when I'm looking through a piece of assembly code. I'll deal with it's moved destination, source. I'll deal with that to not have all the extraneous characters. If you prefer AT&T, that's cool. You can generally, do it in either syntax. Just wanted to give you a heads up so you know what's out there, in case you pull out a piece of somebody else's code and it's like, why does it have all these symbols? She didn't have any symbols in her talk. But yeah, so the move instruction right here where it says move EBX 0x field dead, it means you're moving the value 0x FEE1 DEAD into the register EBX. That's all it means. You're putting a value in that register in memory. Other instructions you're going to use a lot. Interrupts. I'm sure a lot of you know who this guy is. int80 is not just the wrapper in dual core. int80 is probably the interrupt that you're going to be calling the most often if you're doing assembly language in Linux. int80 means make that system call. Now, what the heck is a system call? It's how a program that you're writing interacts with the underlying operating system. For example, let's say you're trying to, execute a print statement in a higher level language. What kind of stuff needs to be done? It needs to find the content that you're printing. It needs to know where to print it. Is it going to standard output? Is it going to something else? It needs to tell the operating system, hey, this is the data to print it. That's all dealt with in a system call. And so what you do when you're running a system call, and I'll show you some concrete examples of that shortly, is get the data where the CPU expects it to be, and then you make the system call with the interrupt. Linux takes that data and will print it to the screen, for example, and then it goes back in and runs through. The other interrupt I wanted to briefly mention, just because it's useful for debugging and playing around, is int3. int3 is just a software breakpoint. You can put it in your code, and it basically, if it's not attached to a debugger, then it's not really going to do anything. But if you do have it attached to a debugger, it tells the debugger, okay, always stop here. So you can then go into the debugger, play around with it, see, okay, what's hanging out in your registers, what's in various places in the stack. There are also mathematical instructions, useful for any kind of, mathematical operations, logical flow, things like that. Add, subtract, multiply, divide. For example, I've got a little bit of code here. Move EAX 10 just puts, binary 10 in EAX. As you could see before, I had the 0x field dead or just 10. You can easily use binary or hex when you're writing these programs. CDQ, it's a slightly more esoteric instruction, although, not that weird. It basically, in this case, it zeroes out EDX. When you're doing a division instruction like you're just about to do, you need to make sure that EDX is set to the same as the sign bit. And since 10 is, a perfectly normal positive number, the sign bit is 0. So CDQ sends 0 all the way through EDX. Then div3, what that means is you're taking the value in EAX and you're dividing it by 3. That's all you're doing. And the quotient is stored in EAX and the remainder is stored in EDX. Or sorry, not EDX. Yes, EDX. No, I said DB. It's early in the morning. I need to make sure I get my letters straight. The quotient is stored in EAX, so that's 3. The remainder is scored in EDX. That's 1. That's all those 3 instructions do. There's also DEC and INC, decrement, increment, useful for looping. You're actually going to see a dec instruction in one of the pieces of code I'm about to show you. So move ECX 3 puts 3 in ECX. Dec ECX just makes it -1. Now ECX is 2. That's all it does. Speaking of loops, you're also going to need jumps. Jump greater than or equal, jump greater, jump less than equal, jump less than. If you have a compare instruction, compare ECX 3, and then say, jump if greater. The way you would do that is if it said jump with greater, and then you put a label in the program, jump greater. If there's a section of your program that you labeled as loop, if it's greater than 3, it jumps to where you put loop. Again, you will see this shortly. There are also jump 0, jump if not 0, jump sign, jump if not sign. Jump 0, jump not 0 is pretty, it's pretty obvious. If you there's a flag in the CPU called the 0 flag, and if you have a comparison that checks if something is 0 and it sets a 0 flag, cool. 0 flag, jumps of 0. Opposite for not 0. I'm sorry, I'm beating a dead horse here. Same thing with the sign bit. That basically checks if a value that you were looking at the previous instruction is negative or not negative. If it's not negative, the sign bit is not set. If it is negative, the sign is set. I told you a bit before about the stack. You have instructions in assembly called push and pop that sort of do the card discard pile thing like I was talking about. Push puts something on the stack. Pop pops something off the stack and puts it into another register for you to use. So in this section of instructions, by the way, that the semicolon, that's the comment character in, at least in NetWide Assembler, which is the assembler that I use just because it's easy to find, it's open source. Anyway, the semicolon is just comments. So move EAX 10, so now EAX is 10. Push EAX, that means you have 10 on top of the stack. Increment EAX, so EAX is now 11. Push puts 11 on top of the stack. And then pop EBX puts the value on top of the stack, which is 11 in EBX. Pop ECX puts the value on top of the stack, which is now 10, because you've already pushed 11 off, into ECX. I mean, that's really it. You're just sticking some things on the stack and taking them off. Pretty straightforward. And then finally, there are function access instructions. You can define functions within your assembly code. Call just means, okay, put the address of the next instruction after the call on top of the stack, and then go into your function. You go through the stuff in your function. You end the function with a ret statement. Ret returns. Now, that's all fine and good, that makes sense as a way of organizing things. But of course it's easy to screw with because it's not like ret actually checks or has any mechanism on its own for checking the sanity that that instruction on top of the stack is in fact where to return to. So if there's some, bizarre stack operations in your function and that thing on top of the stack is not the return address, it's either going to return to something completely junky and it's going to segfault and crash, or it's going to return to your shellcode, say, instead of the actual next instruction after that call statement. So it's a pretty straightforward concept and really easy to screw with. One last thing before we start diving into code is the sections of assembly code. The basic sections of code are data, BSS, and text. Data is just the definitions of constant variables. BSS is basically variables that change while the program is running. So you're allocating space for them, but then dealing with them later. Maybe you're taking user input or doing some math during the program or something like that. Text is your actual executable code. I always found it kind of weird that the executable code section was called text, because when I think of text, I think of, just totally non-executable text files, but text is the section of your code. Now, okay, I filled your brain with all of these, ridiculous instructions and sections of memory, but really, freaking instructions, how do they work? Unlike our favorite little juggalo clowns, it's not magics or miracles or rainbows or magnets. Now it's time to actually see some code. So let me get out of here and open up a terminal. It would help if I could type. You can't see it? Oh dear. This is seriously frustrating because it worked when I connected it to the monitor in the speaker ready room. I did it for exactly this reason, so this would not happen. in something. There we go, mirror displays. All right, so, given all of that wonderful there, I think Failboat, which is the name of this VM, is an apt description of what just went down. Anyway, so we've got here just a really simple piece of C code. It is also an extremely insecure piece of C code. So, if you have Rotten Tomatoes, feel free to throw them at me. But the point here was to just have a very simple example. So even if you've never programmed in C, you could sort of get what was going on. And then it could be easily re-implemented in assembly just to show you, that it's not all that hard to do something in assembly that you can do in C. So here, we've got the main function. We declare a 64-byte array called name. That's where we're going to put our name string. Int I equals 0, that's just an integer variable that we're going to use as a counter for our loop. Printf, please state your name, that just, prints a prompt, please state your name. Get string name, as you can see, there are no checks as to whether name is 64 characters or longer. Totally vulnerable to a buffer overflow. Gets the user input. Then we have our loop here for I equals 0, I less than 3, I plus plus, that just increments I. Printf, oh hi, %n, or %s, comment name, %s, just, that's your format character for the string, name. So if you compile and run this, it takes my name, it says, oh hi, rogue clown, 3 times. Not a very, not a very interesting program, but it does something. It prints things for you to read, it takes user input, and it works. Now let's see it re-implemented in assembly. As you can see here with their section.data, that's for constant variables. What are constant variables there? You have the please state your name, you have the oh hi, and you have the exclamation point and line break at the end. So those are the strings there. There's a string called prompt. DB is the statement that you use to declare a string. Please state your name. I have a comment there that's a 24-byte string. That's useful later because the system call that actually prints that stuff to the screen needs to know how long the string is that it's printing. Same with oh hi, which is an 8-character string, and exclamation mark, DA, which is the, character turn line feed. That's a 3-byte string. Then there's BSS, which I told you before is the section where you reserve space for variables that are changing during the runtime of the program, not constant at compile time. We've got one of those, the name. So resb is just reserve bytes. I'm reserving 64 bytes for the name. And then finally the text, which is the actual code. Underscore start colon, that's just the convention for code running starts here. First syscall that we're going to run is a write system call. Write requires the where it's writing to, what it's writing, how long is that string. EAX, pretty much always when you're running these system calls, what you put in EAX is the number of the system call. I've got, in my list of resources at the end of the talk, where you will find a list of the numbers for the system calls. Write is 4. You'll memorize that if you do much ASM because you'll use it all the time. EBX1, I'm printing the standard output, the screen. ECX is where you put the location of the string. So I call to prompt, and that puts the address of the prompt string, please state your name, into ECX. EDX, 24, that's the length of the string in bytes. And then you call int 80. Again, it's not like you're calling your friend, hey, dual core, what's up? That's the interrupt. At that point, it will have printed, please state your name to the screen. Now it needs to get the data. We'll use a read call for that. Read is syscall 3. 0 is the file descriptor for standard input, generally your keyboard. EDX 64, that's the intended length of the buffer. And then, for ECX is name, that's the address of those reserved bytes that you set aside in the BSS section. Then you tell it in EDX, the intended length of the buffer. Int 80, run that call. It reads until the line break. Then you want to save the length of the string because, it's not necessarily going to be the 64 bytes. It might be shorter. It probably will be shorter. However, when the read syscall executes, it shoves in EAX the length of the string that was actually entered. So I stick that in ESI just to save it because I know I'm going to be tooling around with EAX later for other syscalls. And then I decrement that because that includes the line break at the end. And I don't want it to print, oh, hi, rogue clown, line break, exclamation mark, another line break. Like that would look like crap. So I decrement it so the computer thinks the string's one character shorter. Then I've got the loop here. That comment is wrong. I don't actually set ECX as my index register. I'm setting EDI, which is one of the other general purpose, not a huge purpose except for shoving data type registers. Set that to 3. I do another write syscall. As you can see, move EAX 4 to write syscall. Put it to 1, standard out. Then I print the hello string, oh hi, space. That's 8 characters. Int 80 prints that to the screen. Then I put name, the length of the name, which I have hanging out in ESI, print that to the screen. And then the end line string, the exclamation point, line break, print that to the screen. Then I decrement EDI, which is what I'm using for my counter. Compare it to 0. And then if it's not equal to 0, then it jumps to print names. Basically all the way back up to the loop where I declared print names. If it is equal to 0, it does the exit system call. That's system call number 1. I XOR EBX because if you XOR something with yourself or with itself, that goes to 0. And then int 80, exit with code 0, everything's good, program is done. So I use NASM to assemble it. I use LD to link it, and then it works just like the C code that I showed you. Like we've re-implemented that now in assembly. Thank you. It's the most applause I've ever gotten for printing my name to the screen 3 times. So now that we've done that, let's talk a little bit about, one of the big uses of knowing assembly is being able to write custom shellcode. So let's write some custom shellcode. Okay, for some reason, I should have just looked up there. For some reason, I thought it was going to be mirroring my presenter view, which I'm not really actually using. So where does shellcode come in? Basically, shellcode is just instructions that you're injecting into an already running process. You don't get a lot of the luxuries of writing a standalone program. You're not going to get the chance to tell the computer, oh, put my data section here, and put my BSS section there, and, segment the memory nicely the way I like it. You don't get that luxury. You're shooting it into someone else's code. You are stuck with what they got. So you're injecting a small bit of raw instructions, so hopefully you can get control of EIP, point it to where you've shoved that string of instructions in memory, and let it go. Like, it is basically just one big, or not so big as the case may be, text section. So let's take a stab at shellcode. Back to my terminal. Let's hope this isn't a mess. This is the program we're going to be injecting our shellcode into. It is vulnerable to a buffer overflow attack. You're declaring a 200 character buffer. And if there are less than 2 arguments, i.e. the name of the program and some text for it to echo, it will complain at you and crash. Well, not crash, it will exit gracefully, but it will not run. String copy, that's another thing that doesn't actually check the length of your buffer, therefore vulnerable to a buffer overflow. It copies whatever you put as your command line argument into a buffer and then prints it back at you. That's all that does. Hello is very short. It is less than 200 bytes, but we're going to put more than 200 bytes there and see what it goes. So, I realize I could do a shellcode that actually spawns a shell or does anything like that, but I don't know. You've seen that a million times before, and if you want shellcode that just spawns a shell, you can find that anywhere. The first custom piece of shellcode I ever wrote was a really obnoxious little piece of shellcode where if you had root privileges on the box, it will flash "Hasta la vista, baby" on the screen, wait for half a second, and then turn your computer off. It won't shut it down nicely. It will just boom. Gone. It's a pain in the butt, not useful for pen testing, but really funny as a prank. I don't know. Key there is that it's root, and another thing that's really, really, insecure about this program that I'm running is even though I'm not running as root, I have the simple echo owned by root and the set UID set, so it does not just print your data to the screen, it prints your data to the screen as root. Again, not something you would actually want to run on your own computer, but it makes the shellcode fun. So here, you're declaring it as 32-bit code. Since you don't have access to the BSS section or the data section, what you're going to have to do is get the addresses of your strings the other way. So how are you going to do that? I said before that with a call, it puts the address of the next instruction on top of the stack. Doesn't have to use a ret. The address of that next instruction, if that next instruction is a DB statement that declares a string, boom, there's your address, and you're ready to go to the races. So here, jump 1. I've got something down here labeled 1, call message, and then right below that call statement is DB, hasta la vista, baby. That's the text that prints to the screen. Where's message? It's up here. Pop ECX, that's the address of the hasta la vista, baby string. Zero out EAX, put 4 in there for the write syscall. B1, standard out. ECX, we already have the address of that string from that pop statement. EDX22, that's the length of that hasta la vista string. Int 80, prints hasta la vista, baby to the screen. Now, there's a jump short to 2. Down here, again, we use that call trick because we want here DD, that's a double word length number. And here I've got, 500 million 0.00001. That's the number of nanoseconds I want it to wait. 0, comma 5000001. So that stores a double word that's 0 and a double word that's half a second in nanoseconds, because that's just a time spec struct, which is what the sleep function expects. 0 seconds, 500 million nanoseconds is, well, half a second, basically. Jumps back to power off. Calls NanoSleep, which is a fine-grained sleeping syscall in Linux. Pops into EBX, the location of that time spec struct we declared with that DD statement. XORs ECX, because there's nothing else to do after the interrupt. Moves EAX 162. 162 is just the number for NanoSleep. Runs that, sleeps for half a second. Cool. Then reboot. That's a system call where you've got to feed it a couple of magic numbers, specifically 0x feel dead and 0x Linus Torvalds' birthday. I think the birthdays of his kids also work in this system call, but I'm, using the tried and true Linus Torvalds' birthday. There are a couple of different flags you can feed to that. I'm feeding it the command power off, i.e. don't be nice about it, just cut the power to the stupid computer. Int 80, I put 88, which is the reboot command number. Put feel dead in EBX, Linus's birthday in ECX, the flag for power off in EDX. Int 80, goodbye computer, see you later. I'm just running a bit of code here to get the address of where shellcode, because I basically got my shellcode saved as an environment variable. If you're curious about that, you can talk to me later. I'm getting near the end of my time, so I'm not going to go into the details of how do you craft an exploit, but that's just an exploitation technique to shove a shellcode somewhere, land it somewhere in the NOP sled. NOP, by the way, is just its instruction, 0x90, no operation, just skip to the next instruction. That's where I've got my shell. Actually, I don't think my shellcode is actually saved. I think that looks like a junk instruction. So let me export it right quick and then let's go. I can get my, no, come on. Do not want. It's like faults, but it doesn't turn the computer off. Why not? As you can see, in the hex dump, you got a bunch of zeros there, null bytes. Now this is injected as a string, and what do you think the program is going to do if it sees a bunch of null bytes in there? Ding! It's going to terminate the string. So I've got another version of this that has been recrafted to get all the null bytes out that I'll show you. I told you about the lower parts of the registers. You'll see here move AL, comma 4. If you're putting in the extended value, the 32-bit value, 4 is like 0000000000004, Don't want all those zeros in there, so just moving a 4 to the lowest order part of the byte, that'll get it out of there. The other big trick that I use here is there was that time spec struct that I made with 0 seconds. I can't tell it 0 seconds because, that byte is going to be 000000000, etc. So what I did was I put, FFFF, etc. in there. And then I just, I used an XOR instruction because, an XOR is not a 0 byte. That's just, XORing one location with another, getting the zeros out of my code. We don't have that much time to go through all of the rest of the code, but it's pretty much the same except for using, ALs instead of EAXs, ECXs, EBXs, etc., and getting rid of the nulls in that time spec struct. So let's try this instead and see if it works. I've already assembled it, so let's just try and inject it in the process. Have to export the new shellcode first. And it didn't work. Oh my goodness. I got this to work in the speaker room. The demo gods hate me. I think the address was different, so 9AC, 9B4, why not? No, that's like false too, F9AC. This is really frustrating because it worked right before the talk. It worked like not even an hour ago. And I'm getting a little time on. Can I try this one more time? Oh, I can't try this anymore. So I feel really dumb that didn't work because because right before the talk I was running, I pulled it out of my history and everything. Right before the talk I was able to get it to crash. It printed hasta la vista baby, and it died. So now I look like a turkey, but thank you so much for your time coming out here.